Stretching from the icy waters of the Arctic to the warm currents of the Caribbean, the Atlantic Ocean is a vast, interconnected system, its surface calm belying the immense geological forces at work beneath. The threat that lurks here is not a product of human conflict, but of the planet's restless crust, where tectonic plates grind, collide, and reshape the very face of the Earth. Thousands of kilometers from the American mainland, the volcanic island of La Palma rises abruptly from the Atlantic, its steep slopes and rugged terrain shaped by millennia of eruptions and landslides. Within this dramatic landscape, geologists have identified a unique and potentially catastrophic risk: the western flank of the Cumbre Vieja volcano, a massive structure riddled with deep fractures and evidence of past movement. Scientific surveys reveal that a significant portion of this volcanic ridge is slowly slipping towards the sea, its stability threatened by ongoing volcanic activity, groundwater infiltration, and the relentless pull of gravity. Should this unstable mass, estimated at up to 500 billion tons, suddenly collapse, the resulting landslide would displace an enormous volume of water, sending shockwaves across the Atlantic basin. This scenario, known as a volcanic flank collapse, is rare but not unprecedented. Geological records show evidence of similar events in the distant past, with deposits of marine sediments found high on island slopes, marking the reach of ancient mega-tsunamis. The initial impact would generate a series of waves, each carrying immense energy. Unlike earthquake-generated tsunamis, which typically involve vertical displacement of the seafloor, a landslide tsunami is driven by the rapid horizontal movement of rock and debris into the ocean. The difference in mechanism means the resulting waves can be even more extreme near the source, with initial heights potentially exceeding several hundred meters before dispersing energy outward. Imagine, in a matter of minutes, an entire mountainside plunging into the sea, releasing energy equivalent to thousands of nuclear detonations and sending a wall of water racing away from the impact zone. Near La Palma, the initial wave could reach heights of several hundred meters, obliterating everything in its path and leaving a permanent mark on the island's geography. As the tsunami radiates outward, its energy spreads over thousands of kilometers, gradually decreasing in height but maintaining extraordinary speed, up to 800 kilometers per hour in deep water. Computer models suggest that within 6 to 8 hours, the leading edge of the wave could reach the eastern seaboard of the United States, impacting cities and infrastructure from Florida to New England. The densely populated Atlantic coast with its low-lying cities, ports, and critical infrastructure is particularly vulnerable. Even a wave reduced to 10 to 25 meters in height would be catastrophic, inundating vast areas and overwhelming defenses. The tsunami's approach would be heralded by a rapid withdrawal of water, followed by a series of powerful surges capable of destroying buildings, bridges, and transportation networks in minutes. The aftermath would be devastating. Widespread flooding, loss of power and communications, and long-term contamination of freshwater supplies due to saltwater intrusion. The economic impact would ripple far beyond the immediate disaster zone, disrupting global shipping, trade, and supply chains that depend on Atlantic ports. The story of La Palma and the Cumbre Vieja volcano is a stark reminder of how distant geological events can have direct, profound consequences for societies an ocean away. Modern science employs a network of seismic sensors, satellite monitoring, and ocean buoys to track volcanic activity and detect early signs of instability. But predicting the exact timing and scale of such a collapse remains a formidable challenge. While the probability of a mega-tsunami from La Palma occurring in the near future is considered extremely low, the consequences would be so severe that international agencies maintain ongoing risk assessments and emergency response plans. Understanding the Atlantic tsunami threat requires a multidisciplinary approach, combining geology, oceanography, engineering, and emergency management to ensure that even the most remote risks are not ignored and that coastal communities are as prepared as possible for the unimaginable. La Palma's origins are a testament to the raw, unyielding forces that shape our planet. Unlike islands formed by the slow accumulation of coral or sediment, La Palma was violently thrust from the ocean by the relentless upwelling of magma from deep within the Earth's mantle. The island is the emergent summit of a vast shield volcano, its base hidden far below the Atlantic's surface. Rising more than 20,000 feet from the abyssal plain, La Palma's true scale is masked by the ocean, but its volcanic roots run deep, anchored in the restless boundary between the Earth's crust and the churning mantle below. At the heart of this process lies a mantle plume, a stationary, superheated column of rock that has persisted beneath the Canary Islands for at least 20 million years. As the African tectonic plate drifts slowly over this hotspot, pulses of magma break through the crust, building layer upon layer of volcanic rock and giving birth to new islands in a chain that stretches across the Atlantic. La Palma's volcanic system is among the youngest and most active in the archipelago. Its landscape is dominated by basaltic lava flows, scoria fields, and pyroclastic deposits, evidence of both effusive and explosive eruptions. The island's surface is a living record of its fiery past, with each eruption adding new strata to the ever-growing edifice. The Cumbre Vieja, a prominent ridge running along the island's southern spine, is the epicenter of recent volcanic activity. This elongated structure is a classic rift zone marked by fissures, vents, and cinder cones that trace the path of ascending magma. The ridge's steep slopes, in places exceeding 30 degrees, are built from loosely consolidated ash, fragmented lava, and volcanic breccia, materials that are inherently unstable and prone to collapse. Over countless millennia, the interplay of constructive and destructive forces has sculpted La Palma's dramatic topography. Eruptions deposit fresh lava and ash, building the island higher, while gravity, weathering, and hydrothermal alteration weaken the slopes, carving deep ravines and triggering landslides that reshape the coastline. The island's volcanic history is punctuated by episodes of catastrophic collapse. Massive landslides, some involving entire flanks of the volcano, have left behind steep cliffs and underwater debris fields that extend for miles across the ocean floor. These events are not relics of a distant past. The processes that drive them are ongoing, fueled by the same mantle plume that gave birth to the island. In 1949, the Cumbre Vieja erupted with dramatic consequences. A 2-mile-long fracture opened along the ridge, and the western flank slumped downward by several meters. Geophysical studies suggest this was not a superficial crack, but the surface expression of a deep-seated fault, a potential detachment surface that could one day allow a massive block of the island to slide catastrophically into the sea. Today, the Cumbre Vieja remains a zone of intense scientific scrutiny. Its slopes are monitored for signs of deformation, seismic activity, and gas emissions, clues that may foreshadow future eruptions or landslides. The combination of steep, unstable terrain and ongoing volcanic activity makes La Palma one of the most dynamic and potentially hazardous volcanic islands on Earth. The story of La Palma is far from over. As long as the mantle plume persists, magma will continue to rise, eruptions will reshape the land, and the delicate balance between construction and destruction will play out on a geologic stage. The island stands as a living laboratory, offering a window into the powerful forces that forge and transform our planet's volcanic landscapes. Volcanoes are among the most dynamic and structurally complex landforms on Earth, and their very existence is defined by instability. Unlike solid granite mountains, volcanoes are constructed from a patchwork of lava flows, fragmented ash, and pyroclastic debris, often loosely bound together and riddled with internal weaknesses. Picture assembling a tower from alternating layers of loose gravel, wet sand, and brittle rock. This is a precise analogy for the internal architecture of many volcanic edifices. Each eruption adds new strata, dense lava flows, fragile pumice, and fine ash, all stacked in a sequence that can vary dramatically in strength and cohesion. Over time, water from rainfall or melting snow infiltrates these layers, percolating deep into the edifice and saturating porous ash beds, which can transform into a slick, clay-like material. This process, called hydrothermal alteration, is driven by hot, mineral-rich fluids circulating through the volcano, chemically transforming strong rock into weak, easily deformed clays and minerals. Gravity acts relentlessly on these unstable slopes, constantly pulling at the oversteepened flanks and exploiting any internal weaknesses. Even minor rockfalls and landslides are evidence of the ongoing battle between gravity and the volcano's fragile structure. Ocean island volcanoes like La Palma are especially vulnerable as they rise abruptly from the seafloor, forming steep submarine slopes that are hidden from view but prone to catastrophic failure. The sheer mass of these volcanic islands exerts immense pressure on their foundations, causing the underlying rocks to deform and fracture over time. High-resolution seafloor mapping around the Canary Islands has revealed enormous scars and amphitheater-shaped indentations, clear signatures of ancient collapses. The ocean floor is littered with vast debris fields, giant blocks, boulders, and rubble, evidence of multiple mega-landslides that have occurred over millions of years. Geological studies estimate that more than 200 cubic miles of La Palma have collapsed into the Atlantic, with each event dramatically reshaping the island's profile and the seafloor below. The immediate trigger for a volcanic collapse is often a new eruption, which can destabilize the edifice in several ways. As magma ascends from deep within the earth, it intrudes into the volcano's core, forcing its way through fractures and increasing internal pressure. This rising magma acts as a hydraulic wedge, prying open existing faults and fractures, and further weakening the already compromised structure. The movement of magma is often accompanied by swarms of small earthquakes, which shake the volcanic mass and reduce the friction that holds unstable blocks in place. In 2017 and 2018, hundreds of microtremors beneath Cumbre Vieja signaled the migration of magma, increasing pressure and bringing the western flank closer to the threshold of collapse. The most critical concern at Cumbre Vieja is the enormous, partially detached block on its western side, which is separated from the main edifice by a deep fault. Geophysical surveys estimate this block could contain up to 500 cubic kilometers of material, enough to dwarf any landslide in recorded history. During the 1949 eruption, this block slipped several meters along its fault, a clear demonstration of its instability and the potential for future movement. Scientists fear that a future eruption, especially one occurring low on the volcano's flank, could provide the final destabilizing force needed to initiate collapse. The interplay of rising magma, intense ground shaking, and the immense weight of the block could overcome the frictional resistance along the deep-seated fault, triggering a catastrophic landslide. Should this occur, the entire western flank of Cumbre Vieja would detach as a single coherent mass, accelerating downslope and plunging into the Atlantic Ocean, unleashing a chain of events with global consequences. To truly grasp the catastrophic potential of volcanic collapse, we can examine two of the most scientifically significant eruptions in recent history, Mount St. Helens in Washington state and Anak Krakatau in Indonesia. In the spring of 1980, Mount St. Helens became a focus of intense geological scrutiny as its northern flank began to deform. Magma rising from deep within the earth forced the surface outward, creating a massive, unstable bulge that grew at an astonishing rate, up to 5 feet per day. On May 18th, a magnitude 5.1 earthquake ruptured beneath the volcano, sending shockwaves through the already weakened structure. This seismic jolt was the critical trigger that set the stage for disaster. In a matter of seconds, the entire northern face of Mount St. Helens gave way. The oversteepened bulge collapsed in a colossal landslide, releasing the pent-up energy of the volcano. This event produced the largest landslide ever recorded, displacing over 2.5 cubic kilometers of rock, ice, and soil. The debris surged down the mountain at speeds exceeding 150 miles per hour, carving deep channels and obliterating everything in its path. The sudden removal of the mountain's flank instantly depressurized the underlying magma chamber, triggering a violent lateral blast. This explosion devastated an area of 600 square kilometers, flattening ancient forests and leaving a wasteland of scorched earth. The eruption left behind a vast, horseshoe-shaped crater nearly 2 kilometers wide, a permanent reminder of the mountain's lost summit and the immense power of volcanic collapse. This distinctive crater profile is a hallmark of catastrophic flank failure, exposing the internal structure of the volcano and providing invaluable data for geologists. On the island of La Palma in the Canary Islands, geologists have identified a similar, though much older, horseshoe-shaped collapse scar. This feature marks the site of a prehistoric landslide of truly massive scale. Marine surveys have revealed a vast debris field on the seafloor, evidence that the La Palma collapse was over 50 times larger than the Mount St. Helens event, displacing hundreds of cubic kilometers of material into the Atlantic Ocean. These findings underscore that the Mount St. Helens disaster, while devastating, was only a small-scale example of a process that has repeatedly reshaped volcanic islands throughout geological history. Fast forward to December 2018, when Anak Krakatau, a young and active volcano in Indonesia's Sunda Strait, became the site of another dramatic collapse. Without warning, a powerful tsunami swept across the coastlines of Java and Sumatra. The waves traveled at jet-like speeds, inundating coastal areas within minutes. The impact was catastrophic. Hundreds of buildings were destroyed, and the death toll quickly climbed into the hundreds, with thousands more injured or displaced. What baffled scientists was the absence of any significant earthquake. The region's sophisticated seismic network had detected nothing that could explain the sudden tsunami. Only after analyzing satellite data and conducting detailed marine surveys did researchers uncover the true cause. A massive sector of Anak Krakatau's southwestern flank had collapsed into the sea. This sudden collapse removed over 200 million cubic meters of volcanic material, dramatically altering the island's shape and triggering the deadly tsunami. The landslide displaced an enormous volume of water, generating waves that radiated outward with devastating force, illustrating the efficiency of volcanic collapse as a tsunami trigger. The Anak Krakatau disaster became a pivotal case study for volcanologists and tsunami researchers worldwide, prompting a re-evaluation of volcanic hazard models. The event provided irrefutable evidence that a volcanic flank collapse is not only possible, but is a highly effective mechanism for generating destructive tsunamis, even in the absence of a major earthquake. The aftermath was clear. A vast debris field littered the seafloor, and the volcano itself was left with a distinctive horseshoe-shaped crater, mirroring the scars seen at Mount St. Helens and La Palma. This event fundamentally changed the scientific understanding of volcanic hazards, expanding the recognized risk zones far beyond the immediate vicinity of the volcano. Volcanic eruptions were no longer seen as isolated threats. The Anak Krakatau collapse demonstrated that the effects of such events can travel across entire ocean basins, threatening distant shores with little warning. In tragic clarity, Anak Krakatau showed what a larger collapse at La Palma could unleash, a scenario with the potential to generate a truly massive transoceanic tsunami. The anatomy of a mega-tsunami begins with a catastrophic geological failure. If the western flank of Cumbre Vieja were to collapse, the process would unfold with astonishing speed and force, driven by the immense instability of the volcanic structure and the underlying hydrothermal systems. Scientific models predict that a landslide of this magnitude would involve a colossal mass of rock, potentially between 150 and 500 cubic kilometers, suddenly detaching from the island. This block, equivalent in volume to several Mount Everests, would be set in motion by gravity, lubricated by water and volcanic gases trapped within the rock. As the landmass accelerates, it can reach speeds exceeding 100 miles per hour before it impacts the ocean. The kinetic energy released in this moment is on par with the detonation of thousands of nuclear bombs, focused entirely on the water column below. Upon impact, trillions of tons of rock displace an enormous volume of water almost instantaneously. The energy transfer is so violent that it generates a pressure wave, sending shock waves through both the water and the seabed and creating a massive cavity at the impact site. Unlike a simple splash, this event is akin to dropping an entire city into the ocean at once. The resulting water displacement forms a towering dome, with the initial water mound potentially reaching up to 1,000 meters, over 3,000 feet above sea level. This water dome is highly unstable, held aloft only for a few moments by the sheer force of the impact. Gravity quickly takes over, causing the dome to collapse outward in all directions. The collapse of the water dome generates a series of concentric waves, each carrying a portion of the initial energy. The first waves, closest to the source, are the tallest and most destructive, with heights that can dwarf coastal cliffs. These initial waves would strike the nearby Canary Islands within minutes, with heights potentially reaching several hundred meters. The force is enough to strip away soil, vegetation, and even bedrock, fundamentally altering the landscape. Yet this is only the first stage. The main body of tsunami energy, now organized into a powerful wave train, begins its journey across the Atlantic Ocean. As the tsunami propagates, it travels at speeds up to 500 miles per hour, crossing the ocean in a matter of hours. The wave stretches out, its height diminishing, but its energy spreading over a vast area. In the deep ocean, the tsunami becomes a broad, low-amplitude swell, often less than a meter high, and can pass beneath ships unnoticed. Its wavelength, however, can exceed 100 miles, and the energy it carries remains immense. The tsunami's energy is distributed throughout the entire water column, from the surface to the ocean floor, unlike wind-driven surface waves. This allows it to travel vast distances with minimal loss of energy. To an observer at sea, the passage of a tsunami might be imperceptible, a gentle, broad rise and fall of the water, easily mistaken for a normal ocean swell. Despite its subtlety, the wave is moving with the velocity of a commercial airliner, covering thousands of miles in less than a day. Deep beneath the surface, pressure sensors would register the passing wave as a sudden, powerful anomaly, a silent harbinger of the devastation to come. The tsunami conserves its energy as it races across the ocean, much like a marathon runner pacing for a final sprint. Its true power is only revealed as it approaches land. As the tsunami encounters the continental shelf off the US East Coast, the ocean floor rises sharply, forcing the wave to slow down and compress. The front of the wave decelerates due to friction with the shallower seabed, while the trailing energy continues to push forward, causing the wave to grow in height. This process, known as shoaling, causes the wave to rise dramatically, compressing its energy into a much smaller area and increasing its destructive potential. As the wavelength shortens and the wave slows, the water piles up, transforming the once invisible swell into a towering wall of water. The wave's height can increase exponentially, reaching tens of meters or more, as it nears the coast with the energy now concentrated in a narrow, fast-moving front. In its final moments, the tsunami transforms from a low, broad swell into a vertical, unstoppable wall of water, poised to unleash the full fury of the initial collapse upon the coastline, an event shaped by the relentless laws of physics and the raw power of the Earth itself. Once the landslide occurs and the wave is generated, a silent race against time begins. The Atlantic, stretching over 3,000 miles from the Canary Islands to the American coastline, becomes the stage for a colossal transfer of energy. The tsunami, a pulse of pure energy, would radiate across the Atlantic in all directions, its force shaped by the initial landslide's size, speed, and underwater geometry. The primary wave train, aimed like an arrow at the Americas, would begin its 3,000-mile journey. with the wave's energy concentrated in a broad, fan-shaped swath. Traveling at approximately 500 miles per hour, about the speed of a commercial jet, the tsunami would cross the ocean in roughly 7 to 9 hours, depending on the exact path and ocean depth. But this journey is far from simple. As the wave travels, it interacts with the complex topography of the Atlantic seafloor. Submerged ridges, seamounts, and trenches refract, reflect, and sometimes focus the wave's energy, altering its speed and direction in subtle but significant ways. These interactions can create zones of amplified wave height, as well as areas where the energy disperses, making the eventual impact on distant shores highly variable and difficult to predict with precision. The first waves would reach the easternmost coastlines of North America, including the Caribbean islands and the southeastern United States, between 7 and 9 hours after the initial collapse of Cumbre Vieja. The precise timing would depend on the wave's path and the influence of ocean currents and seafloor features. This time frame presents a monumental challenge for warning systems. Unlike earthquake-generated tsunamis, which are detected almost instantly by global seismic networks, a landslide-triggered tsunami may not be immediately recognized. The Pacific Tsunami Warning Center and its Atlantic counterpart are primarily designed to respond to tsunamis generated by large subduction zone earthquakes. These seismic events produce unmistakable signals, allowing for rapid alerts. A landslide-triggered tsunami, however, is a different beast. The initial event may be silent to seismic networks, with only subtle ground vibrations or acoustic signals. The first definitive sign that a mega-tsunami was even happening might only come when the wave passes over deep ocean buoys, known as dart buoys, which are positioned to detect changes in sea level. These buoys relay real-time data to monitoring centers via satellite. By the time the wave is confirmed by these deep-water sensors, it would have already completed a significant portion of its journey, often more than halfway to the coast. This could leave coastal communities with a terrifyingly short warning window, perhaps as little as 3 to 4 hours to respond, depending on the location of the buoys and the speed of data analysis. The wave would not arrive as a single, uniform wall. Instead, it would manifest as a series of surges, with varying heights and intervals, shaped by the ocean's contours and the coastline's geometry. The complex topography of the ocean floor would refract and focus the wave's energy, creating a varied and unpredictable pattern of destruction. Certain areas, such as headlands and bays, could experience dramatically higher wave heights due to this focusing effect. Projections suggest that wave heights could reach 5 to 6 meters, or around 20 feet in Florida, but could be focused to 7.5 meters, 25 feet, at Cape Hatteras, North Carolina, and an even more destructive 8 meters, over 26 feet, on Long Island, New York. Local topography and offshore features would further influence these numbers. The wave would strike a coastline stretching over 1,000 miles from Florida to Maine, affecting 14 states almost simultaneously. Major ports, power plants, and transportation hubs would all be at risk. This is not a single point of impact like a hurricane making landfall, but a broad, coordinated assault along one of the most densely populated and economically vital regions on the planet. The sheer scale of the affected area would immediately overwhelm any coordinated response. Emergency management systems would be stretched to their limits, with simultaneous crises unfolding across hundreds of miles. Emergency services, communication networks, and evacuation routes would all be put under an impossible level of strain, with infrastructure damage compounding the chaos. The race against the wave is one that for many would be lost before they even knew it had begun. The speed and unpredictability of the tsunami would leave little room for error. The silent journey across the sea would end in a deafening roar, as the energy unleashed by a single landslide reshapes the fate of an entire continent's edge. The arrival of a mega-tsunami would be a cataclysmic event, unleashing forces far beyond anything experienced in modern American history. The sheer scale and velocity of the wave would defy comprehension, with walls of water hundreds of feet high racing toward the coastline at jetliner speeds. Unlike ordinary storm surges, this wave would not simply inundate the shore, it would obliterate it. The leading edge would strike with the force of a moving skyscraper, instantly overwhelming any man-made barrier. Seawalls and coastal defenses, engineered for the worst hurricanes, would be rendered meaningless. The immense hydraulic pressure would shatter concrete, rip steel from its moorings, and erase entire stretches of coastline in moments. The first to fall would be the beachfront infrastructure, hotels, restaurants, and shops, reduced to splinters and swept inland by the relentless surge. Wood-frame homes, so common along the coast, would be no match for the tsunami's power. They would be ripped from their foundations, shattered, and swept up into the churning mass of destruction. The wave would transform entire neighborhoods into floating fields of debris, mixing household chemicals, sewage, and industrial waste into a toxic slurry. The devastation would not be confined to the coast. The tsunami's momentum would drive it deep into the urban core, flooding subways, tunnels, and critical underground infrastructure. In low-lying regions, the water could travel miles inland, inundating highways, railways, and industrial facilities, and triggering secondary disasters as hazardous materials are released. The wave would act as a colossal bulldozer, flattening forests, parks, and anything else in its path, while hurling vehicles and heavy machinery like toys. The debris-laden water would become a battering ram, amplifying the destruction as it smashes through even the most robust structures. Critical transportation links, bridges, overpasses, and elevated railways would be especially vulnerable, collapsing under the combined assault of water, debris, and scouring currents. In mere minutes, the physical landscape would be violently and permanently transformed, with new inlets, bays, and channels carved where neighborhoods once stood. As the initial wave recedes, secondary surges and aftershocks would bring renewed destruction, compounding the chaos and devastation. Floodwaters would rupture gas mains and electrical systems, igniting fires that would spread unchecked across the inundated landscape, fueled by oil, chemicals, and debris. With water mains destroyed and roads impassable, firefighting would be impossible. Fires would rage uncontrolled, further compounding the disaster. As the water retreats, it would scour the land, dragging debris, vehicles, and toxic materials out to sea, leaving behind a landscape contaminated for generations. The physical infrastructure of entire cities, roads, utilities, and communication networks would be reduced to ruins, with only the barest traces of civilization remaining. The financial and structural losses would be staggering, with damage estimates soaring into the trillions and the economic core of the region crippled. Power grids, water treatment plants, ports, and airports would be rendered inoperable, triggering cascading failures across every sector of society. The economic engine of the East Coast would grind to a halt, with commerce, finance, and daily life suspended indefinitely. Supply chains would be severed, leading to shortages of food, fuel, and essential goods across vast areas. Recovery would be a generational challenge, requiring years or even decades of cleanup, reconstruction, and environmental remediation. Some regions would be so thoroughly devastated and contaminated that they would be declared permanent exclusion zones, ghost towns on a redrawn map of America, silent reminders of the tsunami's unimaginable power. The gravest threat posed by a La Palma-generated mega-tsunami is not just its sheer force, but the logistical nightmare it would unleash on emergency management systems across the eastern seaboard. In the best-case scenario, the warning window would be measured in hours, barely enough time for authorities to issue alerts through every available channel, from NOAA weather radios to mobile push notifications and highway message boards. Emergency planners would scramble to activate predetermined evacuation protocols, but the sheer scale, tens of millions in the path, would quickly overwhelm even the most robust systems. Cities like Atlantic City, Miami, and Boston have detailed evacuation maps, but these plans are rarely tested. at the scale a mega-tsunami would demand. Highways and arterial roads would become impassable within minutes, as millions attempt to flee simultaneously, creating bottlenecks that no amount of planning could fully prevent. If the wave were to strike overnight, automated alert systems would be the only hope for waking sleeping residents, but many would still be caught unaware, especially in high-rise buildings and remote communities. The density of the population in low-lying areas means that even a perfectly executed evacuation would leave thousands stranded in the inundation zone. Critical infrastructure, hospitals, power plants, water treatment facilities, are often located near the coast, compounding the risk to both lives and essential services. Communicating the urgency and credibility of the threat to such a diverse and densely populated region would be a monumental challenge, with language barriers and digital divides further complicating outreach. Special provisions for the elderly, disabled, and hospitalized would be difficult to implement at scale, leaving the most vulnerable at disproportionate risk. Public transportation networks, already strained during normal rush hours, would be pushed far beyond their limits, with delays and breakdowns inevitable. For many, the first physical sign of disaster would be the ocean pulling back from the shore, a phenomenon that, while dramatic, leaves only minutes before the wave's arrival. In the aftermath, emergency shelters would need to be established on an unprecedented scale, with logistics teams racing to provide basic necessities to hundreds of thousands of displaced people. Power and water outages would be widespread, as critical infrastructure is damaged or destroyed, hampering rescue and relief operations. Relief efforts would be decentralized, with aid distribution points scattered across hundreds of miles, making coordination and resource allocation a logistical puzzle. Search and rescue operations would rely heavily on technology, as human teams would be unable to cover the vast and hazardous disaster zone quickly enough. Reuniting separated families would require advanced digital registries and biometric identification, as traditional methods would be overwhelmed by the scale of displacement. Access to clean water, food, and medical care would depend on rapid deployment of mobile purification and supply technologies, as traditional supply chains would be severed. The breakdown of sanitation, combined with contaminated water and decomposing organic matter, would create ideal conditions for outbreaks of waterborne and vector-borne diseases. The psychological impact would be immense, with survivors and responders alike requiring long-term mental health support, much of it delivered through digital platforms due to the scale of need. Recovery and reconstruction would demand innovative approaches, from modular building techniques to the redesign of entire urban landscapes with future resilience in mind. Entire cities would face the prospect of being rebuilt from the ground up, with new standards for flood resistance and disaster preparedness. Large swathes of the coast would remain off-limits for months or years as authorities assess structural hazards, environmental contamination, and the safe recovery of remains. The economic consequences would ripple far beyond the disaster zone, disrupting global supply chains, financial markets, and the livelihoods of millions. A La Palma mega-tsunami would test the limits of emergency response, governance, and infrastructure, forcing a fundamental rethinking of how coastal communities prepare for and recover from the unimaginable. When considering the possibility of a mega-tsunami striking the US East Coast, it is essential to move beyond speculation and examine the scientific evidence with precision and care. Risk assessment in this context is a multidisciplinary process, involving geology, volcanology, oceanography, and advanced modeling techniques. The majority of peer-reviewed studies agree that while the western flank of Cumbre Vieja is geologically unstable, the probability of a sudden catastrophic collapse in the foreseeable future is exceedingly low. This conclusion is based on decades of fieldwork, remote sensing, and historical analysis. Geological time operates on a scale far beyond human lifespans. The processes that could lead to a massive landslide are slow and incremental, often taking thousands to tens of thousands of years to reach a critical threshold. Radiometric dating of past landslide deposits reveals that the last major collapses in the Canary Islands occurred hundreds of thousands of years ago, underscoring the rarity of such events. Today, a sophisticated network of monitoring instruments, seismometers, GPS arrays, ground-based radar, and satellite interferometry continuously tracks even the slightest changes in the volcano's structure. These systems are capable of detecting millimeter-scale ground movements, subtle shifts in the volcano's shape, and any unusual seismic activity that could indicate increased risk. To date, all monitoring data indicate that the western flank remains stable, with no evidence of accelerating deformation or precursory seismic swarms that would signal imminent collapse. For a collapse of the magnitude required to generate a transatlantic mega-tsunami, scientists expect there would be a prolonged period of escalating ground movement, increased seismicity, and possibly visible surface cracking, phenomena that would likely be detected well in advance. The 2018 Anak Krakatau event in Indonesia demonstrated that volcanic flank collapses can indeed trigger tsunamis, but the scale and context were vastly different from what would be required at La Palma. While the fundamental physics of landslide-generated tsunamis are well understood, the energy required to send a destructive wave across the Atlantic is orders of magnitude greater than most historical precedents. Eruptions at Cumbre Vieja, such as the one in 2021, are inevitable, but each event is closely analyzed for its impact on the volcano's structural integrity. The 2021 eruption, while significant, did not measurably increase the risk of flank collapse, according to post-event geophysical surveys and modeling. Risk management strategies focus on continuous monitoring, rapid data analysis, and robust early warning systems to ensure that any change in risk level is communicated swiftly to authorities and the public. It is important to recognize that low risk does not mean no risk. Even rare events can have catastrophic consequences, and scientific vigilance is essential. Preparedness measures, including public education, evacuation planning, and infrastructure resilience, are critical components of risk mitigation, even for highly improbable scenarios. The vastness of the Atlantic Ocean and the natural dissipation of wave energy further reduce the likelihood of a mega-tsunami, causing widespread devastation on the US East Coast. But the potential impact justifies ongoing vigilance. Ultimately, the real risk of a mega-tsunami from La Palma is extremely low, but not zero. The scientific community remains committed to monitoring, modeling, and preparing for even the most unlikely events because the stakes are simply too high to ignore. By respecting the power of nature and investing in science and preparedness, we can ensure that even the most remote risks are understood and managed with the utmost professionalism. While the prospect of a transatlantic mega-tsunami captures the imagination, the question remains: has the Atlantic Ocean ever witnessed such cataclysmic waves in its ancient past? To answer this, scientists have turned to the geological record, piecing together clues buried beneath the ocean floor and along distant coastlines. Evidence of past mega-tsunamis in the Atlantic is rare, but not absent. One of the most studied events is the Storegga Slide, which occurred off the coast of Norway around 8,100 years ago. Although technically in the Norwegian Sea, this underwater landslide displaced over 3,000 cubic kilometers of sediment, generating waves up to 20 meters high that struck the coasts of Scotland and mainland Europe. Core samples drilled from the seafloor reveal thick, chaotic layers of sand and marine debris, silent witnesses to the power of the ancient tsunami. Closer to the heart of the Atlantic, the Azores-Gibraltar fault zone has experienced significant seismic activity, such as the 1755 Lisbon earthquake. While the resulting tsunami devastated the Iberian Peninsula and North Africa, its waves, measured at up to 15 meters, attenuated rapidly across the ocean, causing only minor effects as far as the Caribbean. The geologic signatures of this event, found in coastal sediment layers, help researchers understand how energy dissipates over vast distances. Perhaps most relevant to the La Palma scenario is the evidence of prehistoric landslides in the Canary Islands themselves. Submarine mapping has uncovered immense debris fields, some stretching hundreds of kilometers from the island's flanks. The El Golfo landslide on El Hierro, for example, occurred around 15,000 years ago and released as much as 150 cubic kilometers of material into the Atlantic, while computer models suggest that such collapses could have generated local tsunamis with wave heights of 100 meters or more. There is no clear evidence these waves cross the Atlantic with destructive force. Despite these dramatic episodes, the Atlantic's geological history is characterized by long periods of calm punctuated by rare, high-energy events. Each ancient tsunami left behind a unique fingerprint anomalous boulder deposits inland, marine sediments far above normal tide lines, and subtle erosional features on submerged slopes. These geological markers, painstakingly catalogued by scientists, offer a window into the ocean's violent past. Yet no historical or geological record indicates that a mega-tsunami, capable of devastating the modern US East Coast, has ever occurred in the Atlantic in the past several thousand years. The lessons of these ancient events inform today's risk assessments, reinforcing both the power of nature and the rarity of truly global-scale tsunamis in this ocean basin. By studying these echoes from the deep, scientists continue to refine models, improve detection, and build a deeper understanding of how the Atlantic has shaped and been shaped by the forces beneath its waves. Beneath the vast, restless surface of the Atlantic, a silent network stands guard. In the wake of ancient disasters and the ever-present threat of the unknown, scientists have built a sophisticated system of monitoring technologies designed to detect and track tsunamis long before they reach the shore. The journey begins far offshore, where deep ocean assessment and reporting of tsunamis, known as dart buoys, float thousands of meters above the seabed. These unassuming devices are anchored to the ocean floor, connected to pressure sensors that can detect the subtle passage of a tsunami wave. When a sudden change in water pressure is recorded, the data is instantly relayed via satellite to monitoring centers around the world. High above, a constellation of Earth-observing satellites continually scans the ocean's surface. Synthetic aperture radar and altimeters can capture minute changes in wave height and sea level, even from hundreds of kilometers in space. These eyes in the sky provide a vital global perspective, allowing researchers to monitor vast stretches of ocean in near real time. Closer to land, coastal tide gauges quietly record the ebb and flow of the sea. When a surge deviates from normal tidal patterns, these sensors trigger automated alerts, giving coastal communities precious minutes to respond. In many regions, underwater seismometers are also deployed, constantly listening for the deep rumble of earthquakes that could trigger landslides or tsunamigenic events. All this information flows into centralized warning centers, where advanced computer models process incoming data. Here, virtual simulations predict the speed, direction, and potential impact of any detected wave. Interactive maps, color-coded alerts, and automated voice messages are generated for distribution to emergency services and the public. On screens in darkened control rooms, glowing lines trace the progress of simulated tsunamis across digital ocean basins. Automated algorithms cross-check for false alarms, while backup communication systems ensure warnings reach even the most remote communities. Despite their sophistication, these monitoring technologies are constantly evolving. Researchers test new sensor arrays on unmanned underwater vehicles, develop AI algorithms to sift through seismic noise, and enhance satellite resolution to catch even the faintest signatures of a distant landslide. Together, this invisible shield of science and technology stands between the unpredictable power of the Atlantic and the millions who live along its shores. While no system offers absolute certainty, the relentless vigilance of these instruments provides the best defense against the next great wave, a testament to human ingenuity, quietly watching from the depths and the sky. Across the sprawling cities and quiet shorelines of the US East Coast, the challenge of future tsunami risk is met not only with vigilance, but with innovation. As scientists refine the science of detection, urban planners, engineers, and policymakers are turning to a suite of robust mitigation strategies, each designed to strengthen resilience before the next wave ever forms. Computer-generated models visualize elevated seawalls and berms, artfully blending into urban parks and natural landscapes. In coastal towns, animated drone footage glides over newly restored wetlands and barrier dunes, each acting as a living buffer, absorbing and dissipating wave energy long before it reaches homes and infrastructure. Further inland, a virtual cross-section reveals critical infrastructure. Power substations, hospitals, and water treatment plants strategically relocated to higher ground. Automated systems reroute power and shut down vulnerable pipelines at the first sign of an approaching wave, minimizing cascading hazards. On screen, a digital map highlights the expansion of vertical evacuation structures. Reinforced towers, parking garages, and public buildings engineered to withstand the force of a tsunami, offering safe refuge above the inundation zone. Animated signage and lighting systems guide simulated crowds to these elevated shelters, ensuring a rapid, orderly response even in the dead of night. A sequence of 3D infographics details the integration of advanced, AI-driven hazard mapping. These models continuously update risk zones based on the latest geological surveys, population density, and infrastructure changes, feeding actionable insights directly into municipal planning software. Along the virtual coastline, fleets of autonomous drones and amphibious vehicles patrol for signs of shoreline erosion and unauthorized construction, transmitting real-time data to command centers. Here, city officials review holographic dashboards, running disaster drills and scenario planning exercises, each iteration refining protocols and uncovering new opportunities for resilience. In the absence of people, the focus shifts to the symphony of systems, resilient architecture, adaptive landscapes, and the quiet hum of technology, all working in concert to shield the coast. Through relentless preparation, strategic investment, and the seamless integration of cutting-edge science, the East Coast builds a future where the next great wave meets not devastation, but determination. The screen fades into a high-resolution satellite image of the Canary Islands, focusing on the rugged western flank of La Palma. A digital clock in the corner begins its countdown T-0, initiation of the collapse. The simulation begins. A 3D model illustrates a massive section of volcanic rock detaching and thundering into the Atlantic Ocean. Sensors embedded in the digital landscape register a colossal displacement of water. Within moments, a ring of energy ripples outward, growing rapidly across the open sea. The perspective shifts to a global map. Animated wave fronts expand, their leading edges marked by color-coded bands representing wave height and speed. As hours pass, the simulated Mega-Tsunami races westward at jetliner speeds over 500 miles per hour, its energy undiminished by the vastness of the Atlantic. Next, a cross-section of the ocean floor reveals the tsunami's undersea profile, a long, low wave in deep water, barely perceptible to passing vessels. Automated buoys, represented by blinking icons, detect and relay the sudden anomaly. Real-time data streams to virtual command centers, where algorithms confirm the event's scale and trajectory. As the wave nears the continental shelf, the simulation zooms in on the US East Coast. Here, the water shallows abruptly. The tsunami's energy compresses, wave height surges, and the wall of water transforms, rising, steepening, and accelerating toward land. A series of computer-generated sequences follow the wave's arrival in rapid succession. In New York City, elevated seawalls and automated flood barriers deploy in sync, diverting and absorbing some of the impact. Animated overlays show water surging through lower Manhattan's streets, flooding subway entrances, but slowed by the city's new defenses. Further south, in Miami, the simulation highlights restored dunes and mangroves, their dense roots fracturing the wave's energy, saving inland neighborhoods from the brunt of the flood. Critical infrastructure, previously relocated to higher ground, remains untouched as power grids automatically reroute and emergency lighting activates. On the digital model, evacuation towers and vertical shelters fill with animated crowds, tiny icons moving with purpose, guided by illuminated signage and synchronized alerts. As the water recedes, drone footage simulations reveal the aftermath: debris fields, altered coastlines, and pockets of standing water. Autonomous vehicles begin rapid assessment, mapping flooded areas and scanning for structural damage. Within hours, virtual reconstruction models propose immediate repairs and long-term adaptations, integrating lessons from the simulated event. The scenario concludes with a wide-angle view of the coastline, changed but not broken. Data overlays summarize the event, wave height, impact zones, and response times. Through simulation, the unthinkable is studied, understood, and prepared for, transforming fear into foresight and vulnerability into resilience. The aftermath of a mega-tsunami is not measured solely by the scars it leaves on cities and infrastructure. Beneath the surface, the wave's force initiates a silent transformation of marine and coastal ecosystems. Aerial drone footage glides over the coastline, revealing newly carved inlets and sandbanks where forests once met the sea. Saltwater inundation stretches far inland, submerging freshwater marshes and transforming them into brackish lagoons. In the tidal zone, mats of uprooted kelp and seagrass drift ashore, their tangled roots testament to the wave's reach. Underwater, high-definition cameras track the suspended plumes of silt and debris. The normally clear water is now clouded, sunlight struggling to penetrate. Coral reefs, once vibrant with color and life, appear battered, broken branches and overturned colonies scattered across the seabed. Yet, some resilient species, sponges and hardy anemones, cling to the fractured substrate, already reclaiming their place. Further offshore, a school of fish weaves through a new underwater landscape. The tsunami's force has shifted boulders and created crevices, forming unexpected habitats. For some marine creatures, these changes offer sanctuary. For others, the upheaval spells displacement and loss. On the sands, ghost crabs emerge from collapsed burrows, surveying a beach reshaped by the ocean's power. Turtles, returning to nest, find altered shorelines, some familiar nesting grounds washed away, new ones formed elsewhere. Seabirds circle above, drawn to pools of stranded fish and organic matter left by the retreating wave. In the estuaries, nutrient-rich sediments settle, triggering blooms of plankton and algae. This sudden abundance fuels the food web, but also threatens balance. Oxygen levels dip, and sensitive species struggle to adapt. Over time, the environment begins its slow recovery. Mangrove shoots pierce the mud, stabilizing the shoreline. Hardy grasses reclaim the dunes, anchoring shifting sands. The ecosystem, forever changed, embarks on a new chapter, marked by loss, resilience, and regeneration. Through the lens of nature, the mega-tsunami's legacy is written not just in destruction, but in the relentless drive of life to adapt and endure. As the immediate ecological shockwaves settle, the focus shifts to the world stage, where the enormity of a transatlantic mega-tsunami demands a coordinated international response. Animated world maps illuminate, tracing the interconnected coastlines of Europe, Africa, and the Americas. Digital overlays reveal a vast web of early warning systems, each node representing a seismic station, ocean buoy, or satellite relay. Cut to satellite imagery, clusters of ships rerouting away from projected impact zones, their paths traced in glowing arcs across the Atlantic. In ports, time-lapse footage shows rows of container cranes pausing mid-operation as automated alerts ripple through global shipping networks. On a bank of monitors, international weather and disaster agencies, NOAA, the European Commission, the Caribbean Disaster Emergency Management Agency, exchange encrypted data in real time, their logos flashing as files transfer seamlessly across borders. A split-screen montage highlights diverse approaches. In Lisbon, a robotic drone launches from a coastal station, deploying underwater microphones to monitor aftershocks. In Dakar, a solar-powered tsunami siren is automatically triggered, its signal relayed via satellite to remote fishing villages. Along the US eastern seaboard, programmable traffic signs flip to evacuation instructions, while in the Azores, high-resolution weather balloons ascend, collecting atmospheric data for predictive modeling. Zooming out, a dynamic infographic visualizes multinational drills, digital avatars representing emergency responders in reflective vests, practicing coordinated search and rescue, debris clearance and supply distribution. Shipping containers bearing international aid, marked with flags from Canada, Brazil, Germany, and Morocco, arrive at temporary logistics hubs, their contents sorted by autonomous cranes. Throughout, the narrative is one of seamless interoperability. Automated translation algorithms convert alerts into dozens of languages. Shared databases allow scientists from 5 continents to analyze real-time oceanographic data. Even as the Atlantic's waves reshape coastlines, the digital infrastructure of global cooperation weaves a safety net, one designed not only to respond to disaster, but to anticipate and mitigate its impacts. In this new era, the resilience of nations is measured not just by their individual strength, but by the depth of their collective readiness. The Atlantic, once a barrier, becomes a bridge, uniting humanity in the face of nature's most formidable challenges.